Welcome to this video on Stage 1 Mathematics Uber Investigation. In this video, we're going to have a look at something called a Voronoi diagram. More specifically, we're going to have a look at what a Voronoi diagram actually is. We're going to have a look at why it's useful for us in this context. And finally, we're going to have a look at how we can generate them. But firstly, let's consider the context of the investigation that we're currently working on. Now, the investigation itself involves the problem such that you are located somewhere on a map and you pull out your phone to catch an Uber to somewhere. Now, you simply click order and eventually a car will show up and pick you up to take you where you want to go. But the question is, if there are multiple cars scattered all around the map, which one gets a ride? Which one's going to pick you up? Now, the way in which we're going to answer this problem is we're going to use something called a Voronoi diagram. Now, a Voronoi diagram is simply a means of segmenting area of a shape. So a Voronoi diagram is simply a means of segmenting area. Now, considering this example here, we've got multiple cars scattered all around the map and here's a pickup zone. So the question is, how can we apply a Voronoi diagram to segment this map up to decide which car gets to pick up this person? Now, before we do anything, let's have a look at what a Voronoi diagram will look like. Now, if I jump over to Desmos here, I've inputted all of our data into this Desmos program. Now, I've got different cars set to different areas, so 2, 4, 6, 7 cars. Now, if we turn on a Voronoi diagram that's already been pre-rendered, we're going to get something that looks like this. So notice that for each area or each polygon, we only have one car. So each car has its own area and there's only ever one car in any given area at any given time. Now, the implications of this is such that if you order an Uber and you're located in the area or within the polygon that's been assigned to the car, then what you can say is you can decide which car is going to pick you up. So this is effectively how the Uber algorithm will work when cars are being assigned to passengers. They look at the area that the car is covering and the closest car in that area will get the ride. Now, this isn't always the way in which it's going to work out. Voronoi diagrams can be generated in any number of ways, but it's simply a means of representing how we can break or how we can partition the area up and how we can fairly assign cars to different passengers. Now, the question at hand is, how can we generate one of these diagrams? Now that we've had a look at what a Voronoi diagram is, and secondly, why it's useful in this context, let's have a look at how to generate one. More specifically, let's have a look at how we can generate this one. Now, this Voronoi diagram here, it's an algorithm designed about the distances between the 2 points, and it takes roughly 5 to 6 steps to actually do. Now, the nice thing about this algorithm I'm about to show you is that it's repeatable in that you can arrange all of these points in any which manner that you'd like. You're always still going to come out with a usable and functional Voronoi diagram. So jumping back over to the OneNote here, the way in which we're going to do this is it takes roughly 5 to 6 steps. Now, the first step is you're going to join all of the dots together. So all of these vertices, they're going to get connected together with line segments. So what I'm going to do is I'm going to grab a red pen and I'm going to start connecting all of these points together. Now, of course, for this one, I'm only doing it freehand. When you're doing it, you're going to be, well, the first one you could do, it could be freehand, but when you're going to be doing it, remember, you're going to be calculating the actual equations of these lines. So y equals mx plus c. Now, another thing to notice is this is going to get really messy. As all of these lines are populating the paper here, there's lots of collisions. Now we'll be dealing with these as well. Now I could go on and put all of the possible lines in here, but for the next step, it's simply not required to draw every single line here, so long as we draw the shortest lines. Now the next step here is we're going to have a look at where the lines actually collide with one another, and we're going to start removing or deleting the longer of the two lines when they collide. So looking at these lines here, notice that the first collision we can see are these two here. Now looking at the lengths of the lines, we simply by inspection we can see that this line here that I've just deleted is the longer of the two, so that one needs to go. Now of course, when you're doing these calculations, to actually prove that that line's longer, you're going to use the distance formula. So distance formula being the difference between 2 points, all squared, and then all square rooted, like so. So you would use this out, or you'd use this formula here to determine which line is longer numerically. So going through and removing all of the lines that collide. So notice that next ones that's colliding are these two, and the longer of the pair are this one. Got these two over here, easy one. Then these two here. Hard to see by inspection. I would say that it's D, E, and F, this one. Alright. And then what else do we have? Actually, I'd say it's the other one. That's there to stay. And then the final one is these two here. And of course, you can easily see that it's this one here that's the longer of the two. So what we're left with is a diagram with line segments. So the shortest paths between each vertex, whereby the lines themselves cannot cut one another. So the paths cannot cross over one another. Now, our next step for generating a Voronoi diagram is we need to calculate the midpoint between, or the midpoint of all of these line segments. Now, to do that, we use the midpoint formula, of course. Midpoint, and it's simply the average of the x. Now, doing this via visual. Alright, now that we've got our midpoints, our next step is we need to draw lines that run perpendicular to our red lines that cut the red lines or intersect the red lines at the midpoint, so these points here. So we're going to see something that looks something like that. So draw perpendicular lines that intersect that midpoint. Now, of course, to do the perpendicular, we're going to get y equals mx plus c, and our normal is going to be -1 over the gradient, like so. And to calculate c, then you need to figure out how you're going to do that. Are you going to use general form, or are you going to use a different form? A simple way to do it is you can go c is equal to, you can pick y1 take -m multiplied by x1, so the midpoint coordinates. So what we're going to get are lines that are going to look something like, and once again it's going to be a big mess of different lines, which is not ideal, but it's all a part of the journey of implementing our Voronoi diagram. Now, rather than drawing all lines all across the page, which isn't going to be helpful, we'll leave it there and we'll go to the next step. And the next step along our journey is, whenever we see these lines here, we firstly want to identify which line it belongs to, and then as soon as we see the first collision, the line segment on the opposite side of the collision to its originating line that it came from, we delete that part. So remove portion of line after collision. So it looks a little ambiguous, so just watch. notice that if we're taking, let's say, this green line over here, if we want to get rid of some part, identify the line that it originates from. So it's this red one here, its midpoint. We go across to its first collision and notice it's colliding over here. So what we're going to do is scrap this part of the line. So I just got rid of my red line, like so. That's better. So what we've got is part of a line. Now the next step is we have to do that for all of them. So next line we can look at is, say, this red line over here. This green one's going to originate like so, and its collision is over here as well. So the part of the line we're going to get rid of is this part over here. And then finally this line here, we're going to get something like that. So what you can start to see emerging is there's a pattern. So this line here, removing the next part, we're going to get to this part, which needs to go, following the pattern along. What you can see is the Voronoi diagram is starting to emerge from all of this chaos, and we can start skipping steps and simply freehand in a Voronoi diagram like so. Now when you're implementing this, you'd be using all of your mathematical calculations. So you'd be using your distance, midpoint, then actually calculating the equation of a line and then putting in the domain and the range. But for this one here, we can simply get away with freehanding. When you're doing yours, your hard copy, then you do all the maths to back it up so you can actually do it in the computer. Now to finally do or complete this diagram, we're simply going to remove the red lines, and thus what we're left with is simply a beautiful looking Voronoi diagram. So notice that all of the cars are allocated their own little area. So not a very complicated algorithm to use, and quite robust in that this will give you a solution to most cases that you can come up with. Now, implemented on the computer, jumping across to the Desmos solution to this problem, what we can see is how the steps involved are all done over in here. So starting off, we have our points listed on the map. We connect all of the points together using the shortest path method. So whenever you see intersecting lines, you remove or you delete the longer of the two lines. So you're simply left with a diagram here that shows you the shortest paths, shortest non-intersecting paths between all of the vertices. After that, you calculate the midpoints on all of these particular lines, and then finally you draw in lines that are perpendicular to the original lines here connecting the points together that cut these all line segments at the midpoint. So thus we're left with our Voronoi diagram like so.